Okay, good morning. 11 a.m. Everything seems to be working, and we can start. Continue. Continue diving deeper into Lagrangian formalism. And finally, today we will start looking at examples, real examples. But in the previous class, we introduced what? We introduced some fundamental stuff, right? So we introduced Hamilton's principle. We introduced, of course, Lagrangian as the difference between kinetic and potential energy, right? So that's how we construct a Lagrangian of any system. And then we introduced also Lagrange equation, which is basically equation of motion of a system. And a solution of that Lagrange equation makes action integral or just action stationary, right? So that's how it's all connected. But we introduce all that for a system without any constraints. So you remember how we introduced, for example, Lagrange equations. We pick, actually we introduce in a very strange way, right? So basically like digging a tunnel from the Newtonian formalism to the Lagrangian formalism, right? Basically using Newton's second law, right? And anyway, we introduced Lagrange equations for a system which was exposed to a conservative force. So as a result, we can introduce potential energy, right? But there were no any constraints acting on a system, right? So there was no any ropes or cords or rods connecting a system to something, right? Or surfaces, not a single constraint, right? As a result, so now we need to add constraints to the system. And of course, legitimate question. So if we are going to add constraints, it means we're basically adding forces of constraints. And forces of constraints, they are not conservative, right? Like a normal force or tension or something else, right? So they're not conservative. So we cannot introduce it into the system as the potential energy and just rewrite the Lagrangian as T minus U, and now we will have an additional term, additional potential energy term. So now, of course, now it's a big question. So what is going to happen to all our this Lagrangian formalism if a system is exposed to some forces of constraints, right? So, for example, right, is the Lagrange equation going to have the same form, right? Or, for example, is a solution of the Lagrange equation going to minimize the action integral, the action, right? And so, of course, strictly speaking, all that must be derived, must be proved, right? So, or maybe adjusted, the whole formalism, right? Okay, so, and that's what we're going to discuss basically today, right? So, system, and we're going to add to a system constraints. Okay, and then, yeah, we will I will say what we will adjust. But for now, let me just write the major point, right? So now let's add constraints to a system, pretty much. That's the major sentence in today's class. Okay, so let me write. Now let's add constraints to a system. To a system. So that's the major point of today's class. And first, let's see what will happen to coordinates. Right. So let's start with, you know what, let me write immediately the title of this small section, and then I will describe what is that titled Generalized Coordinates. Now let's introduce a generalized coordinates. Generalized coordinates. So what is that? So let's assume that we have some completely arbitrary, I don't know, system. Oops, I just picked a new marker and it takes a little bit of time to make it work. So n system consisting of n point masses, n particles, right? So let's say we have these, right? So masses. So we have, let's assume that we have n particles. Right. So if there are no constraints, yeah, and this is three-dimensional space. Okay, let me add n particles in 3D space. I will just press harder on the marker, right? It will get better very soon. So n particle in 3D space. How many coordinates do we need to describe this system? 3 coordinates for this particle, 3 coordinates for that, 3 coordinates for this, x, y, z, for example, right? So if you have n particles, then of course you will need 3n coordinates. And of course, in order to describe this system, you need completely, right? And of course, all those 3n coordinates are going to be linearly independent if there are no any constraints, right? Okay, so now let me write that down. If no constraints, first bullet, if no constraints, constraints, then we need 3n linearly independent coordinates. But what if we have constraints? For example, maybe one particle is suspended and oscillating. Or maybe what if there is a rod connecting, for example, these two particles? Or maybe there is a surface, right, which restricts the motion of the system, right? So what if we have one constraint? If, for example, let's say we have a rod connecting these two particles, if there is a constraint, then it means that you can connect coordinates, right? And number of linearly independent coordinates will be reduced by 1. If you have 2 constraints, the number of linearly independent coordinates will be reduced by 2, and so on. So if you have k constraints, then number of linearly independent coordinates, these linearly independent coordinates, will be reduced by k. So if you have k constraints, the number of linearly independent coordinates will be 3n minus k, right? So now if, let me write a new bullet, right? So now if, which we wrote, if there are k constraints, if there are k constraints, then you will have only n small, which is 3n minus k, linearly independent coordinates. Right? Okay, and of course, in the Lagrangian formalism, you can write Lagrange equation only for linearly independent coordinates. Right? So it means that now, in order to apply Lagrangian formalism and write down the Lagrange equations, we need to reduce number of coordinates that we need to describe the system, because now we have only n small linearly independent coordinates. So now, basically, we just need to make a transition from 3n coordinates to 3n minus k coordinates. And basically, we're making transition from an old set of linearly dependent coordinates, right, So if you have k constraints, of course, 3n are going to be linearly dependent, and only 3n minus k linearly independent coordinates. So basically, you are going to make a transition from a set of linearly dependent coordinates, 3n, to a new set of linearly independent coordinates, 3n minus k. Right? And this new set of linearly independent coordinates is called generalized coordinates. This new set is called a set of generalized coordinates. And of course, the coordinates themselves are called generalized coordinates. That's the major point. So if no constraints, you have 3n, but if there are constraints, of course, 3n are going to be linearly dependent. And you need to reduce it to a new set of linearly independent coordinates, and only then you can write Lagrange equations for each of those linearly independent coordinates. And this new set of linearly independent coordinates, and this new set of linearly independent coordinates are called generalized coordinates. Right? So that's the definition of generalized coordinates. And now let me write down something about this. Right. Okay. So we need to reduce, since definition of generalized coordinates is one of the essential in the Lagrangian formalism. So let me write down. So we need to reduce number of coordinates from 3n linearly dependent coordinates. All right. We usually start, you will see in the examples, we will usually start with Cartesian coordinates. Every time I will first write down the Lagrangian using x, y, z for each coordinate, for each particle. And then we will make a transition to a new set of coordinates, which, of course, will be linearly independent and which are generalized. So from 3n linearly dependent coordinates to a new set of 3n minus k linearly independent coordinates. Called generalized coordinates. Right. Okay, I will put in the brackets, so generalized coordinates. Generalized. And in order to make this transition from the old set of linearly dependent to a new set of linearly independent coordinates, of course, every time we will have to write what is called transformation equations. Using transformation equations. So we are going to do it many, many times. And basically, when we're going to write transformation equations, that's the place where we're going to use our constraints. That's the only place where forces of constraints and constraints are going to appear. And after that, usually after writing transformation equations, you can forget about all those constraints. But of course, we will look at the examples. We will start looking at examples. Okay, so now let me write something in terms of kind of in equations. So again, as I said, most of the time we will start with Cartesian coordinates, right? So, so from R alpha, so that's a set of dependent coordinates, x alpha, y alpha, z alpha, where alpha spans from 1 to n. right? So that's what you need if there are no constraints. And of course, in that case, if there are no constraints, this set of all these x, y, and z's will be linearly independent. But if there are constraints, of course, this set is no longer going to be linearly independent. So we need to move to a new set of generalized coordinates. So from these guys, we will have to go to, okay, probably let me make it shorter, to Q. Which subscript I use? I. All right, so Qi, it will be from Q1 and all the way to Qn, where n, of course, this small, 3n minus k. Right, so where I spans from 1 to n, which is 3n capital minus k. Right. And of course, where n, it's a space. So in this case, three-dimensional. Sometimes it can be two-dimensional, right? So it's not a big deal. Right, and again, the major point, so these guys are linearly dependent, and these guys, all these Q's, are going to be linearly independent. Independent. And that's the major difference between this set and that set. And again, it's in the case when there are constraints imposed on the system. And again, as I said, transformation equations. So of course, every time we will have to write transformation equations, which will allow us to move back and forth, right? Because you can move there, all right, solve the problem using these generalized coordinates. But at the end of the day, when you solve the problem, you might still want to know what happens to your system in your old, conservative old coordinates, x, y's, and z's. We will look at one example probably next class where we will do that. Right. So, and of course, in order to make this transition, we need to write transformation equations, right? So, transformation equations, back and forth. So first, for example, if you want to move back from generalized coordinates to this old set, of course you can use this, which depends on Q1, Qn. Sometimes time dependence is possible. I will talk about this time dependence maybe like in 15 minutes. So, but still, in general, it's possible to have time dependence in a transformation equations. And in the opposite direction, inverse, or maybe, in the opposite direction. So, which way I can write? So Qi, I use, Qi. And of course, this will be a function of all these Cartesian coordinates, R1, R2, and so on, Rn, right? So this will lead us from generalized to the old coordinates, and this will lead us from the old to a new set of generalized coordinates, right? So that's one of the most important term in Lagrangian formalism. Every time before you can start writing down the Lagrangian and start solving problem using Lagrangian formalism, every time you have to make a decision which generalized coordinates you're going to use. Right? So now let's look at a few examples of generalized coordinates and transformation equations. Right? So first, let's look at simple pendulum. Right? Examples. Let me write down. Again, these are small examples in order to show which generalized coordinates can be used for some systems, but we're not going to solve the problem completely, no. We will start probably doing that at the end of the class, closer to the end of the class, today's class. All right, so first one, simple pendulum. Okay, finally marker writes nicely with a good contrast. Right. So let's assume that this is a ceiling, right, and the pendulum of mass m and length L. Right. So first we need to understand how many generalized coordinates are needed. So let's run this analysis. So if no constraints without, which way I wrote, just a second. Yeah. So without constraints, no constraints, if the system don't have constraints, it means there is no chord. We have one point mass m in two-dimensional space. So in two-dimensional space, so we'll have 2 times 1. So we need 2 coordinates. If there are no constraints, then of course you will need 2 linearly independent coordinates to describe the system. For example, x and y. Right. No constraints, then you will need 2 linearly independent coordinates. Right. For example, x and y. But in our case, we have one constraint. Right. This rope of length L. So in our case, we have, we have one constraint. Okay, that chord. Right? So as a result, of course, now number of linearly independent coordinates will be reduced by 1. 3n minus 1. But of course, now we have two-dimensional space. I immediately removed z-axis out of the game because it's immediate obvious constraints. Right? So it will be 2 minus 1. We need 1 generalized coordinates to describe this system. So 2-dimensional space, 1 particle, minus 1 constraint. So we need 1 generalized coordinate. So we need 1 generalized coordinate, and it's a 1-dimensional system. Right? Okay, so which coordinate to use? It's up to you. There are no any strict rules which coordinate can be used in this case. You can still, for example, use only x. Or y. Okay, let me introduce coordinate system first of all. Because I started using x's and y's, but I haven't introduced them yet, right? Let me position origin over here, and this is, let's say, y, and this is x. And since we are using Lagrangian formalism, you remember, you must use an inertial reference frame. So Lagrangian formalism cannot be applied for a non-inertial reference frame. So that's why I position the origin and the reference frame, I ground it at the point of suspension. Right? So let me emphasize that this is inertial. Inertial RF. Right. Okay, so yeah, back to our decision about which generalized coordinate can be used. Again, there are no strict rules. It's sort of like an art, right, based on experience. You can use x, nothing wrong with that. You can use just y, nothing wrong with that. But of course, you know, the most convenient coordinate, every time sort of we can say we have to wisely pick the best generalized coordinates possible. In this case, of course, the best coordinate is the angle measured from the vertical direction, from the vertical line. So this will be the best coordinate. Which one I used? Theta? Phi. Okay. Phi. Right. So this is the best coordinate. Of course, you can use that other angle which complements this to 90 degrees. Right. But the angle, of course, is the best. Okay, so now, once you decided which generalized coordinate to use, now you have to write transformation equations, which basically will allow us to move from our x and y to phi, right? And of course, every time in the problem, if you use Lagrange equation, all right, show your generalized coordinate or coordinates in the diagram properly, or even just state in the problem, because that's the essential part. So now transformation equations. So we picked a new set of coordinates, linearly independent. And now we just need to write down transformation equations. So now transformation equations. And as I said, that's the only place where you are going to use your constraints, forces of constraints. And after that, you can forget about them. After that, it's basically calculus. So transformation equations. So what? X. This is y coordinate, right? So this is x coordinate. So we can write, so x equals L times what? Sine phi, right? So first transformation equation, and the second, y equals L times cosine phi. And maybe over here I should have written, so phi, that's our generalized coordinate, and this are our transformation equations, right? And so, strictly speaking, we're not going to solve this problem. But I would first I would write Lagrangian in terms of x and y's, kinetic energy minus potential energy, and then I would just use this transformation equation to replace all x's and y's in our Lagrange equation with phi, to replace x and y's with phi. Right? And then as a result, of course, your Lagrangian will be a function of phi and phi dot possible, right? So now, next example. First, I thought about skipping it, and then I decided, okay, let's discuss it also. A double pendulum. It's a very straightforward problem, but so tedious, so lengthy, usually, double pendulum. So the second example, double pendulum. You know what, before I go into the next example, double pendulum, again, look, right now, transformation equations do not have time dependence. So there is no t. But here you remember, okay, I should have also added t here. It's possible. I started talking, but I didn't try it. So, but right now, there is no time dependence. Right. After this example, there will be an example with a time dependence. So double pendulum. So let's say, again, this is the ceiling. All right, so let's say this is the point of suspension. So the first pendulum of mass m1, I think this one. Yeah, let's call it m1. And then there is a second pendulum underneath of this one. So this will be m2. Right. Okay, so let's say we want, for example, to describe this system, double pendulum. Again, as usual, you need to introduce an inertial reference frame, like in the previous case. And of course, I will position the origin at the same point, so y, x, right? So again, two-dimensional space. Immediately, I will remove z from the game, because that constraint is obvious, right? So immediately, I assume that we have two-dimensional space, right? Two-dimensional space, so we'll have n 2n minus k. So now we have two-dimensional space, two particles. So if no, and of course, two constraints. We have this, okay, I need to write, so this is L1 and this is L2. And now we have two constraints, this chord and that chord, right, which reduces reduce a number of linearly independent coordinates. So 2 times 2, number of particles 2. So it will be 4. If we don't have constraints, of course, we would need 4 coordinates to describe the system, x1, y1, x2, y2. But now with 2 constraints, it will be 4 minus 2, 2. So we will need 2 generalized coordinates to describe this system. Right? Again, let me write the same, similar. All right, so no constraints. If no constraints, oops, no constraints, then of course you will need 2 times 2, 4 coordinates, x1, y1, x2, y2. But with 2 constraints, of course, you will have 2 times 2 minus 2. So again, 2-dimensional space, 2 particles minus 2 constraints. I just wrote this down for 2-dimensional space. So it will be 2 generalized coordinates are needed. Which one? Again, it's up to you. You can use, for example, I know, x1 and y2, or x2 and x1, or y2 and y1. It's up to you, right? So there are no strict rules which coordinate to pick. But of course, again, it's, as I said, it's a mixture of art and experience, right? You should pick the best coordinates to simplify solution. And in this case, again, the choice is obvious. It's a phi 1 and phi 2, which measures angle from a vertical direction. So this will be, right, so phi 1, and this will be phi 2. So 2 generalized coordinates, so let's say phi 1 and phi 2. So these are our generalized coordinates. And transformation equations. Usually transformation equations, most of the time, it's just simple geometry. You just draw a nice picture, so that everything will be visible in front of you. And then just using right triangles, right? So again, simple geometry, like in the first case. Now, what? This is y1, this is x1, this is x2, and this is y2. Okay, you know what, x1 overlaps with that, and this also. Let me use different color, for example, let's say blue. So this will be x1, and this will be x2, and this is y1 and y2. And so now just simple geometry. So what, x1 and y1 will be exactly the same like in the first example, right? So now transformation equations. So x1 equals to L1 times sine L1 times sine of phi 1, and okay, let me write y1 first. y1 equals L1 cosine phi 1. So that's the first set of transformation equations. And now the second one. Okay, x2 equals. So x2, it will be x1, right? So you see x2 equals x1 and plus this small, this section, which is L2 times sine of phi 2, right? So it will be x1 plus L2 sine of phi 2. So it will be L1 sine phi 1, L1 sine phi 1 plus L2 sine of phi 2. So next transformation equation. And now the last one. So we have 4 coordinates, and now we need to replace them with 2 coordinates, phi 1 and phi 2. Right, so now it's a y2. So y sub 2, it will be y sub 2, it will be y1 plus this section. So it will be y1 plus L2 cosine phi 2. Okay, so just to rewrite y1 from here. So it will be L1 cosine phi 1 plus L2 cosine phi 2. Okay, so these are transformation equations. Again, I would, if we decided to solve this problem, of course, first I would write Lagrangian in terms of x1, y1, x2, y2, and then I would grab these transformation equations, differentiate them with respect to time because we have x1, y1, x2, y2, x1 dot, y1 dot, x2 dot, y2 dot in the Lagrangian, right? And plug that into Lagrangian, and after tedious, right, very tedious transformation, we would end up with a Lagrangian written in terms of phi 1 and phi 2. Right? So that's why I usually don't solve this problem, because it's very straightforward, but so kind of tedious. Okay, so now the next example. And again, look, these transformation equations, again, do not depend on time. And now let's look at the example where transformation equation is going to be time dependent. Okay, I guess it's time to erase this part, start erasing this part, and look at another example. Again, just we're not solving, we're just picking generalized coordinate and writing transformation equations. Again, when you start first using the marker, also difficult to erase. Okay, it looks decent. So I don't have to wash it. So the next example, so that was 1, 2, and now number 3. So let's assume that we have a car or railroad car travels in a certain direction along a straight line and with constant acceleration, right? So which way? That way. Right. Okay, I will probably draw it here. Yeah. Okay, so let's assume that this is our car. Okay, let me make it slightly taller. Right. And the pendulum. So let's assume it accelerates that way. So A equals constant acceleration. Let me draw the surface. Right. Okay, inside, let's position a pendulum, just simple pendulum. Of course, it will be deflected, let's say, this way. So M and length of the chord L. Right. Okay, so we want again to write transformation equations for this case. Right. First of all, we need to pick again reference frame, and again it must be inertial. Again, let me emphasize. So it's again inertial. Right. So it means that over here you cannot position your reference frame into the card. I remember it's one of the first questions I had on a qualifier exam. There was a system, right? So there was a block sliding, so I was asked, so Can you position coordinate system, for example, over there on that, attached to that block? And of course, if I would say yes, then of course it would be actually quite not silly, big mistake, big mistake. So it means that I need to ground my reference frame somewhere. Let me ground in this way. I will just stick y-axis into the ground over here. So this is x, this is y. Again, you can choose any coordinate system you want. You have that universal freedom, right? But I will pick it this way. Again, let me emphasize that this is okay, I will write here inertial. Since I need that space over there, so I decided to move inertial information about system being inertial to there. Right, and also, let's assume that this card was over here at t equals 0. Right, so which way I wrote it? T equals 0. So at t equals 0, the card was here, and initial velocity was 0. So this is the origin. That's where I positioned the origin. At the point where the car was at the initial moment of time. And of course, let's assume that the initial velocity was 0. So now we just need to write coordinates of this particle. Basically, we just need to write transformation equation, coordinates of this particle using through the generalized coordinates. And generalized coordinates over here, generalized coordinate, is the best one is, let me use this. So first let me draw this vertical line, and of course the best coordinate is this angle. Phi. I think I used phi. Yeah, phi. And of course you can also introduce position, for example, of this suspension point and treat it as the variable, right? But in this case, I wouldn't recommend that. Since we have basically, we know the motion of this car, the car moves with the constant acceleration, right? And we know how to describe that. So let's use that information, right? And write down coordinate of that suspension point using basically physics 1 knowledge from physics 1, right? So basically I can write, so let's say, let's denote this coordinate of that point as x s sub s. S maybe a suspension point of suspension. So and that x sub s, it's 1 over 2 a t squared. Again, you can introduce additional generalized coordinates, right? Additional coordinates to define position of that point. But the problems like this, right? Usually, if you can easily predict motion or position of, or you can describe one of the coordinates, just better use it, right? To reduce complexity of the problem. Okay, so I just use knowledge from physics 1. Okay, so then as a result, now I can write coordinates of this bob. So this will be, let's call it, yeah, that's x, and this will be y. Right? So now we need to write x and y in terms of this generalized coordinate, and of course information about the point of suspension. Again, simple geometry, right? So what? X, let me write, so x, this x, right, equals. So it will be this distance from the origin to point of suspension, x sub s, and then minus L times sine of phi. So subtract this distance in order to get this x. Right? Again, every time you see in all 3 examples, writing transformation equations, just simple geometry. But of course, the diagram must be nice so that you can see the geometry. So x sub s minus x times, or not x, L. L times sine phi. Sine phi. So as a result, I can write 1 over 2 a t squared minus L sine phi. So that's first transformation equation. And now the second one. Y coordinate of that bob. So y equals, in this case, point of suspension, of course, coordinate of the points of suspension is not going to be involved because y sub s is 0. Right? So it will be just, in this case, L times cosine phi. And since I picked y-axis downward, so that is positive. So L cosine phi. So these are transformation equations. And what is the major fundamental difference between these transformation equations and this one? Of course, systems are different. You can say, what a stupid question. No, but the major fundamental difference between these between this set and those sets of transformation equations, that this system depends on time. There is a time dependence. So transformation equations are time dependent. Okay, you remember over here, I erased it. I should have left it. I didn't realize it. All right, so when I wrote down general form transformation equations, I said that it's possible to have time dependence. These guys, there's no time in these guys, but over there, time dependence. So, and can I ask you, this system, is it kind of isolated, independent? Again, isolated or independent from the outside world? And it's not. Because the system is driven, acceleration is maintained constant. It means that there is something acting on the system, and as a result, acceleration of the system is constant. So this system is not isolated. Basically, it's being driven. And whenever you have a system which is being driven, for example, like in next class, we will look at the loop with the point mass, right, which will be capable of sliding on the loop, and this loop will be spinned with constant angular velocity. So if it's spinning, the system is no longer isolated, right? So it means that energy is dumped into the system. Over here, the same story. The system is driven. The energy is being dumped into the system. And whenever this happens, whenever the system is driven, not isolated, every time there will be time dependence in your transformation equations. But these systems, no, they're not driven, right? So they live their own life, right? They don't care what happens outside, no frictions, no drag forces, nothing, right? So no driving forces. They live their own happy life, natural, organic, right? No external influences. So as a result, these transformation equations, which do not have time dependence, are called natural. Right? So what should I write about this? Actually, not just transformation equations, generalized coordinates. Yeah, I should have been more precise. So generalized coordinates, in this case, for example, phi, it's a natural generalized coordinate, right? Organic. Right. And phi 1, phi 2, also natural. These guys, these not. Right. It's not a big deal if you forget this term, and most likely in 5 minutes you will forget the term natural. It's not a big deal, as long as you realize that, understand, if there is a time dependence, it means that it's a driven system, right? So it means that there is a transferring of some energy from external world into the system, or maybe in the opposite direction, right? So, but those systems, they live their own life, happy life. So the next terminology, the next term is very important because you're going to see it quite often, right? Holonomic system. So what does it mean? So if you have a system, mechanical system, right, which you want to describe, and number of generalized coordinates equals to a number of degrees of freedom. If these two numbers are the same, again, number of generalized coordinates and number of degrees of freedom, if these numbers are the same, then that system is called holonomic system. Right? And of course, if number of generalized coordinates that you need is larger than number of degrees of freedom, then of course it's a non-holonomic. But in both of these courses, undergraduate classical and graduate classical mechanics, every time we were going to discuss only discuss holonomic systems. So not usually, no, not usually, just in a Goldstein, the book which we use in the graduate level course, there is one example, all right, which is sort of conceptually discussed. Example of a non-holonomic system, where he discusses why number of generalized coordinates that you need to describe the system is larger than number of degrees of freedom, right? So that's the only example. We're not going to look at that. So from now on, we need to remember the meaning of holonomic system, because we're going to use it quite often, right? But we're not going to use a non-holonomic systems. But let me write down anyway this definition of this term. The system is called holonomic if the number of degrees of freedom is equal to the number of generalized coordinates needed to describe the system. Okay, so now let me separate this. Right. And now I will put a new bullet. So the system is called holonomic. Holonomic. Again, it's one of those terms which, it's better to remember because you're going to see it quite often. It's called holonomic if the number of degrees of freedom, if the number of degrees of freedom is equal to a number of generalized coordinates, is equal to the number of generalized coordinates, of course, needed to describe the system. I will skip that. Okay, and as I said, from now on, all the systems are going to be holonomic. Okay, so now next, so we introduced generalized coordinates, transformation equations, awesome. All right, now sort of back to the same question which I raised at the very beginning of this class. So what about fundamental stuff? You remember Hamilton's principle? Yeah, it's fundamental, but we derived Lagrange equations for a system which did not have any constraints, right? So what if a system has constraints? Is the Lagrange equation going to have the same form? And the same, again, the next question, logical. We saw before that a solution of the Lagrange equation makes action stationary, action integral stationary. But what about what about the case with constraints? Is a solution of Lagrange equation, is a solution going to make action stationary in this case? Of course, very important questions, right? And I used to go through the derivation, right? So 2 pages of small handwriting, right? And probably half an hour of derivation in class. I remember I did it only once. I think in 2012 or 11, I don't remember exactly, right? And students were looking at me with round eyes, right? So what, are you completely crazy, right? And maybe I still am, right? Oh, sorry. But after that, I decided, no, it's not worth of spending that time, half an hour. And plus, I don't feel like it's a very elegant derivation and proof, very nice. So I decided, no, it's not worth of going through this one more time. So after that, I usually just write down a couple of sentences. So basically, the bottom line is if forces of constraints or constraints are imposed on the system, then basically all that fundamental stuff which we introduced for a system without constraints can be used for a system with constraints. So the form of the Lagrange equations are going to be exactly the same. Again, solution of the Lagrange equations are going to minimize action still, or not minimize, makes action stationary, right? But of course, most of the time we're talking about minimization. But still, strictly speaking, it should be, we should say stationary. All right, where the transformation, where are the constraints where are the constraints going to appear? I already mentioned in the transformation equations. When you write these transformation equations, these, that, this, so basically tacitly we use constraints. We use these chords, right? We use that chords, right? In order to write transformation equations. So that's the only place where forces of constraints are going, where the forces of constraints are going to appear. And after that, when you write down transformation equations, you can forget about those forces of constraints and constraints. And then again, that's one of the beauties of Lagrangian formalism. You just write down transformation equations, and after that, the rest is straightforward. So now let me write maybe one additional sentence, two, right? So I will just write without a proof. Now let me put a red bullet, so very important, right? And probably I should underline this holonomic. And so without a proof, Lagrange equations, so basically the form stays the same, work for any, again, holonomic system. So now from this point, I will be using this word holonomic this, holonomic them, that. So for any holonomic system with constraints. So basically the same Lagrange equations can be used. Right. And of course, I will emphasize without a proof. Without a proof. If you desperately want, you can read the book. Right. So Lagrange equations, all right, work for any Lagrange equation, okay, ends, plural. Lagrange equations work for any, okay, holonomic system with constraints. Okay. So basically it means that we can still use the same Lagrange equations to solve our behavior with the system with constraints. And as I said a few minutes ago, so the constraints appear only when you write transformation equations. So let me write that down also. Constraint forces do not appear explicitly anywhere in the equations, right, except transformation equations. So the constraint forces do not appear explicitly, of course, explicitly anywhere in the equations. Okay, let me write, except transformation equations. And again, not forces appear in transformation equations, but presence of the constraints. Because again, every time, the geometry which we use based on the constraints.
Professor, when is the next exam? What would it
Okay. The next exam will be, usually I give it after the 3 chapters. So the first exam was after 3 chapters, and the second exam after 3 chapters. So after this chapter. So we will probably spend this class, then next class, and maybe a little bit of the, maybe like in a week and a half, we will finish this chapter about Lagrangian. Yeah, so then I will need to give you some time for the homework, and then there will be exam. So the second midterm exam will be about oscillations, chapter 5, calculus of variation, chapter 6, and then chapter 7, Lagrangian formalism. So probably 2.5 weeks. It will be closer to the final exam. Usually there are like a couple of weeks between the final exam and the second midterm exam.
All righty, thank you.
Yeah, so that's basically happens every semester. Right? That's what happens. So okay, now after this, now we can start attacking any problem. Of course, only holonomic problems, systems. So I used to solve Atwood machine. It's reasonably straightforward. You can read the book by yourself. It's after a couple of years, I decided no, it's not worth of efforts. Too simple. Now let's look at the examples, real examples. So we'll start from scratch with finding generalized coordinates, transformation equations, then Lagrangian, Lagrange equations, and so we will solve it completely. All right, so I guess I will start erasing this, right? So we have a cylindrical surface, infinitely long cylindrical surface of radius r. So it starts from that infinity and goes to that infinity, right? So first example. And a particle, single mass, point mass, moves on the surface of that cylindrical surface. There is no gravity. There will be only 3-dimensional Hooke's force acting on the particle, right? No friction, right? And of course, this system has constraints. Cylindrical surface. There will be normal force, right? So it's a typical example of a system with constraints. Okay, so now let me probably draw a picture. So let's say this is my cylindrical surface. And let me position coordinate system immediately. It will be more convenient for me to draw. All right, so I will position origin over here somewhere, right? Of course, if it is an infinitely long cylinder, so just pick a point somewhere. And so this will be y, x, and z, right? And our point mass on the surface. So it cannot get through the surface. So that's point mass m. Of course, position of that point mass can be defined using position vector. Right? So let me write, so n on a cylindrical surface. cylindrical surface of radius r. So what else is given? The fact that it's exposed to a three-dimensional Hooke's force. Right. So first, let me put a new bullet. So which way I wrote? 3D Hooke's law. So F equals minus KR. And we're going to position the origin, okay, not the origin, basically the reference point in this case, right? Reference point. Of course, we're going to introduce potential energy, right? Okay, let me write immediately. You can easily do that, right? So U equals minus integral of F dot dr from, okay, let me write immediately, from 0 to R. So basically, immediately, I will position the reference point at the origin, right? So this will be our reference point for this potential energy. Okay, and it's equal 1 over 2 kr squared, where r, okay, you know what, let me remove this vector sign. So, of course, you understand that it can be used. Okay, it's this r over here, right? So basically r in spherical coordinates, but we're not going to use spherical coordinates. We're going to use cylindrical coordinates, right? So, but you remember, this r is not r from cylindrical coordinates. So that's potential energy, right? So great. Then no gravity, let me remind you, no gravity, gravity and friction. Because presence of the friction force, which is not a force of constraints and not conservative, so it will change the Lagrange equation. It will change the Lagrange equation. So as a result, pretty much not a single problem in this semester we're going to discuss. Not a single problem will have friction force. Right, so what next? Yeah, normal force. Normal force, of course, is present here, but we just discussed. Not discussed, yeah, discussed, but we did not prove. I erased that. So forces of constraints do not change the Lagrange equation, right? And do not change, do not change Lagrange equation. Right, so let me remind you about this. So normal force, of course, is here. Normal force, of course, it's a force of constraints. Force of constraints. Right. Normal force does not affect or does not change a Lagrange equation. Okay, equations, because most likely we're going to have more than one Lagrange equations in this system. Okay, we still have 5 minutes. Okay, so now we have to make a decision which generalized coordinates to use, and let's run the same analysis. So we have three-dimensional space, one point in three-dimensional space. So without constraints, of course, we will need three coordinates, linearly independent coordinates, if we did not have constraints. But we do have one constraint, and it means that 3 minus 1 constraint, we will need two generalized coordinates. Okay, let me write something about this. So without constraints, if we did not have constraints, then we will need three coordinates, for example, x, y, and z, or maybe rho phi z or r phi theta. But with one constraint, So we'll have 3 minus 1, 2 generalized coordinates. Which one? Again, it's up to you. There are no strict rules how to choose them, how to pick them. But we're going to use cylindrical coordinates, so we're going to make a transition to that. And I would pick angle phi and z. Okay, so let me show them first. So let's see. So this is z. Okay, I need to probably use, I will use red. Usually I use red to show generalized coordinates. So let's say this will be our first generalized coordinate z. And then angle phi. So angle phi, we can find it by dropping this, then this, right? And angle phi is that. So these are our generalized coordinates. So two generalized coordinates, phi and z. Okay, so and now let's first we'll write down Lagrangian in terms of Cartesian coordinates, and then I will write transformation equations. I will skip transformations. I will discuss it. I will describe it later. So, so first L Lagrangian, of course, it's a T minus U, kinetic energy minus potential energy. So kinetic energy, first I will write, as I said, in Cartesian. So it will be x dot squared plus y dot squared plus z dot squared, right? Square of the velocity in Cartesian coordinates. And minus our potential energy minus 1 over 2 k r squared. Yeah, of course you can write it as x squared plus y squared plus z squared, right? Maybe I should write it. Right, x squared plus y squared plus z squared. So strictly speaking, that's our Lagrangian. But again, we wrote it down in terms of x, y's, and z, but they are dependent. All these x, y, and z's are dependent. So we need to reduce number of coordinates to to phi and z. So how? We need to write transformation equations from this x, y, z to phi and z. So now from x, y, z, we need to go to phi and z. So these are generalized coordinates using transformation equations. Okay, and transformation equations are basically, those are equations which allows us to move from Cartesian coordinates to to cylindrical, right? So, let's start with x. Of course, it will be. Okay, let me introduce rho. This distance is rho, and of course, that distance rho equals to r capital, which is given, right? So as a result, this is also r, this distance. Yeah. So as a result, x will be equal to r times cosine phi, r capital times cosine phi, y equals r capital times sine phi, right? That. And z, z. Z stays z, right? Because we decided to use basically cylindrical coordinates. These phi and z are cylindrical. So z is z. So these are our transformation equations. So let me write underneath. Transformation equations. And of course, strictly speaking, all right, so what do you have to do at this point? you have x, y, and z to replace this with phi and z. And of course, you will have to write x dot y dot z dot over here and plug it over here. Of course, you will have to do x dot equals y dot equals z dot equals, right? But we're not going to do it because it's tedious and it's not needed, because we all know velocities in cylindrical coordinates. So we can write in this case immediately. But strictly speaking, that's what we're supposed to do, right? And of course, in most of the problems, we are going to use this procedure. But in this case, there is no point. We all know and we all must remember velocities in, for example, cylindrical coordinates, velocities in spherical coordinates by heart. Right? Of course, you don't have to, but it's better to remember, actually. It's better to remember. Right? And of course, after this, we can write Lagrangian easily. Right? Okay, let me write them down, Lagrangian. Right? And then we'll call it a day. I thought maybe I will postpone writing the Lagrangian to the next class. No, it's very simple now. So L will be equal m over 2, right? Okay, let me write the velocities in coordinates of the velocities in cylindrical coordinates. You remember it's r dot, then, okay, rho dot, phi dot, and z dot. That's what I was talking about, right? So as a result, in our case, rho is constant. It's 0, and this rho equals to r capital, right? So it will be r capital phi dot squared, then plus z dot squared. So that's kinetic energy. And potential energy r squared, it will be z squared plus r capital squared, right? So this right triangle, right? Again, remember, these are, it's a spherical coordinate, basically, which, of course, we're not going to use. We're going to use cylindrical. So minus 1 over 2k z squared plus r squared. So we can write it, you see, immediately. But, of course, if you follow this procedure, after maybe 10 or 15 minutes of tedious work, you will end up with that anyway. But in this case, there is no point of not wasting, but spending time in this way. So that's the Lagrangian of this system. Okay, enough.